Welcome to the Deep Dive. This is where we take a whole universe of ideas, articles, dense philosophy, old experimental notes, and we try to weave them into one single, clear story.
And today, wow, we are going way back to the Islamic Golden Age. We're talking the 9th, 10th, and 11th centuries.
A period that didn't just, copy and paste old knowledge. They were building something totally new. They were fundamentally systematizing and really revolutionizing how we even define reality.
Our mission today is, it's a big one. We're trying to connect three ideas that, on the surface, seem totally unrelated.
What are they?
First, this massive Herculean effort to organize all of human knowledge. Second, the surprisingly high-stakes philosophical vocabulary that they had to invent to do it.
And the third?
And the third is the actual physics of how you see, a revolution in optics that happened in an experimental lab. We are literally tracing a line from the most abstract definition of matter all the way to how you physically know how far away that tree is.
So we're going from the philosopher's study, thinking, what is stuff, to the scientist's lab asking, how do we see that stuff? It's a huge journey.
It really is. Okay, let's unpack this.
All right, before we get into the deep philosophy, let's just ground ourselves. I mean, literally, I want you to imagine you are standing outside.
Okay.
You're in a massive, totally flat landscape. Like, think of a desert salt flat, or maybe a huge empty airfield. It stretches out, perfectly uniform, all the way to the horizon.
Total emptiness.
Almost. There's one single thing way, way off in the distance. A tiny, dark mountain, maybe, or just a little flag planted out there.
And you see it instantly. You know it's far. Your brain it gets it.
Yeah.
That sense of distance, that three-dimensional space just stretching away from you, It feels so solid, right? So calibrated and just knowable. Like it's geometry hardwired into your brain.
It does. It feels completely innate. But here's the claim, the really provocative idea at the heart of our deep dive today, and it shatters that feeling. For hundreds of years, the single most dominant, most rigorous scientific theory on this planet for how your brain knows that flag is far away. It had nothing to do with abstract math. It wasn't some internal brain processing.
But what was it?
It was all about the flat, continuous physical surface beneath your feet.
Wow. Okay, that is a pivot. Because the ancient world, drawing on the Greeks like Euclid and Ptolemy, they had the emission theory.
Right, the idea that your eyes are like little laser pointers.
Exactly. They thought your eyes actively shot out these invisible visual rays that went to the object, bounced off, and came back with the information. That was the established science for centuries.
Kind of an amazing idea. It makes vision this active, almost aggressive act. You're going out and getting the world.
And that's what makes the 11th century corrections so absolutely radical. This new theory just flips the whole script.
Yeah.
It says correctly that light rays are received by the eye. But then it goes a step further.
This is the ground part.
This is the ground part. It linked seeing distance not just to light, but to the physical calibration of that surface in between you and the object. You know the flag is far because you're processing the vast continuous ground between you and it.
Okay, wait. I could push back on this right away. Why couldn't they just use geometry, like basic triangulation? Why does the physical, visible ground have to be the thing?
That is the perfect question, and it's the exact question that separates the 11th century from the 17th. We're going to get to that.
Right.
But for these early scholars, working in a world based on Aristotle's physics, you had to observe the physical world. Abstract math wasn't enough.
And this idea, this radical ground theory, this came from one person.
Primarily, yes. The 11th century scholar Ibn al-Haytham. In the West, they called him Alhazen.
And this wasn't just some, niche idea he had.
Oh, not at all. This is where it gets really interesting. His work, the book on optics, it became the gold standard. It was translated, copied, studied. It became the dominant theory of vision across Europe for almost 400 years.
400 years.
This was not a footnote. It was the foundation. But to really get why his experimental breakthrough was so huge, we have to go back a few decades earlier. We have to understand the intellectual chaos that this other guy, Farabi, had to fix first. A chaos that was all about the language of science itself.
So to get to the 11th century lab, you first have to understand the beautiful mess of the 9th and 10th centuries.
A beautiful mess is the perfect way to describe it. This was the Great Translation movement, centered in places like Baghdad. Scholars were just grabbing everything they could find.
Aristotle, Galen, Euclid.
Everything. From Greek, Syriac, Persian, Sanskrit. all being translated into Arabic. It was this incredible flood of raw information.
It's like downloading the entire internet from 3 different alien civilizations at once.
And the problem wasn't bad translations. The problem, the real villain here, was linguistic chaos, a philosophical jargon crisis.
What happens when you're trying to talk about a big Greek idea like essence or potentiality in a language that just doesn't have a word for it yet?
You get a mess, a really high-stakes, confusing mess. The scholars, they basically used 3 different and conflicting strategies. It created this linguistic Tower of Babel that made any real philosophical debate almost impossible.
Okay, 3 strategies. Let's break those down.
Strategy 1 was transliteration. They just took the Greek word and sort of squeezed it into Arabic. The best example is the Greek word hail, which originally just meant wood or forest. But Aristotle used it to mean prime matter, the raw, formless stuff of the universe. So it becomes the Arabic loanword hayula.
So if you're a student back then, you're reading about physics, you see the word hayula, and you have to remember, okay, that sounds like a Greek word for wood, but it actually means the fundamental potential of all things.
Exactly. It's a mental hurdle every single time. Then there was strategy 2, borrowing. They'd pull words from other nearby cultures, like Persia.
Okay.
So they took the Persian word jawar, which literally meant jewel or gem, a beautiful, precious thing, and they repurposed it to mean substance or essence, the thing that exists all on its own.
That's fascinating. Using jewel for substance, it gives it this feeling of being something core, something precious.
It does. It carries a conceptual weight. And then strategy 3 was just repurposing native Arabic. They'd take a normal, everyday Arabic word and dedicate it to a super technical, philosophical meaning.
Like what?
The word mada, which just meant like a supply or a resource, it became the main technical term for matter.
Okay, so you've got hayula, jawar, and mada, all floating around, all being used by different people in slightly different ways to describe reality.
Yeah.
How do you build a science on that kind of quicksand?
You can't. And the stakes were huge. If you can't agree on what substance means, what stuff fundamentally is, then the entire structure of Aristotelian physics and metaphysics, the very thing you just spent 150 years translating, it's useless. You can't critique it. You can't build on it.
And this crisis is what leads to these books of definition, basically giant glossaries to get everyone on the same page.
Exactly. And this is where Farah comes in. He dies around 950. He's not just another philosopher. He's the system architect. He steps into all this chaos and basically says, okay, everyone, we need a standard operating procedure for knowledge.
They called him the second teacher, right? After Aristotle.
They did, because his genius for systems was obvious to everyone. His legacy is really 2 big things. First, works like the Book of Letters, where he's analyzing the nuts and bolts of logic and grammar. And second, his masterpiece, the enumeration of the sciences.
And that wasn't just a list.
No, it was a whole framework, a required structure for all knowledge. He brought Aristotelian rigor to everything. He said, look, a good definition has to tell you 4 things about the object. The 4 causes.
Its matter, its form.
Its matter, what it's made of, its form, what gives it its shape, its efficient cause, what made it, and its final end, its purpose. He didn't just give them a dictionary, he gave them the logic to build the dictionary.
So let's apply that to the main problem, defining matter and substance. What did Farabi do to fix that vocabulary?
He stabilized it. He made choices. And he really preferred the native Arabic terms when he could. He championed mada as the one consistent term for matter, the potential, the stuff that receives a form.
And he just sidelined the Greek word hayula.
Pretty much. He just let it fall out of use because it was confusing.
Yeah.
And then he clarified the difference between mada, matter, and jawar, substance.
This is the key distinction.
This is the huge conceptual leap he clarified for everyone. For Farabi, jawar, substance, is something that exists on its own. It's unqualified, self-subsistent. But, and this is the important part, in the real world, nothing is just pure jawar.
It's always a combination.
It's always a combination. Mada, the matter, is the potential that supports the form. They can't exist on their own. You never trip over a pile of pure potential or see a disembodied shape. You only ever see a jawar, a substance, which is the complete package.
So that one distinction, mada is the potential, jawar is the real thing.
Yeah.
That created the stable ground for everyone who came next.
Exactly. It's like, think of it like trying to build a new video game engine. But half your team is using old Latin words for collision mesh, and the other half is using Japanese terms they borrowed, and everyone's calling the same thing 3 different names.
The game would never even load.
It would never load. Farabi came in and wrote the official coding standards. He created the dictionary so that the next generation, guys like Ibn Sina, could stop arguing about the words and actually start building theories.
He was literally creating the metadata for reality.
Yeah.
But tell me more about his enumeration of the sciences. How did he organize everything? Was it alphabetical?
No way. The structure was the argument. He split all human knowledge into 5 main categories based on how abstract they were. It started with, number 1, linguistic science, grammar, language, the tools you need to think.
Okay, so tools first.
Tools first. Then number 2, logic, the rules of thinking. Only after you have the tools and the rules can you get to the content. Number 3, the preparatory sciences, math, geometry, astronomy, music. Then 4, natural science, physics, stuff about bodies and motion. And finally 5, civil science, politics, law, theology.
Wow. So he puts grammar and logic before math and physics. He's saying you have to agree on your definitions and your methods before you can even claim to know anything about the world.
Precisely. And that systematic thinking went all the way down to basic physics, like the question of empty space. The void.
The vacuum problem. What do you think? Did he believe in Kala, the void?
He wrote a whole treatise on it, on vacuum. And his answer was a hard no. He was a classic Aristotelian on this. Nature abhors a vacuum. He argued that air is a continuous body and it would just instantly expand to fill any space.
So the very idea of a perfect nothing was just incoherent to him?
Totally incoherent. And that rejection of empty space in favor of a continuous physical reality, that's the perfect setup for the experiments that came next.
Okay, so Farabi builds the system. He defines the terms. He organizes all of knowledge. That frees up the next generation, people like Ibn al-Haytham, to start asking different questions.
Exactly. They can move from what is reality to, okay, given this reality, how does it work? How does it interact?
From the definitional to the experimental.
And that's Ibn al-Haytham. He's the master of that pivot. He died around 1039 in Egypt. He took Farabi's stable platform and basically invented what we now recognize as the modern scientific method.
Rigorous, repeatable experiment.
Totally. He built what was, for all intents and purposes, the first real systematic physics laboratory.
And his main target was optics, vision. We talked about the old emission theory, rays shooting out of the eye. How did he take down a 2,000-year-old idea?
With geometry and physics. It's all in his masterpiece, the book on optics, from around 1027. He just showed how the old theory didn't work. He'd say, look, if rays are coming out of your eye, the geometry says you should be able to see the entire sky reflected in one tiny mirror.
Which you obviously can't.
Which you obviously can't. So he makes the great correction. Vision happens because light rays are received by the eye. And his work was so thorough, it basically created a new field of science, moving from the simple Greek idea of optica to this much bigger experimental science of perspectiva.
He wasn't just defining vision, he was defining light.
And how it moves. He argued it travels in straight lines. He demonstrated its properties using things like the camera obscura, the pinhole camera. He was in a dark room, measuring and manipulating light, treating it like a physical thing that follows physical rules.
Let's talk about the failures, though. The scientific method isn't always a straight line to the truth. And his work on the rainbow is a perfect example of being kind of conceptually trapped.
It's a fantastic example. The rainbow was a huge puzzle. Aristotle had this theory that it was a reflection from a sheet of clouds acting like a giant convex mirror. Haytham wanted to crack it with his new experimental method.
So how do you build a rainbow in a lab in the 11th century?
It was a pretty clever setup. He took these big glass spheres, filled them with water, and then passed sunlight through them. He was trying to mimic how water droplets in the air work.
And what happened?
This is the fascinating part. The experiment worked, he saw the colors, but his conclusion was wrong. He mistakenly thought the spheres were acting like concave mirrors.
So he was stuck on reflection.
He was completely stuck on reflection, trying to force his observation to fit a modified version of Aristotle's old idea. He totally missed the real magic, which was refraction, the bending of light as it goes into and out of the water.
And that wasn't figured out for another couple hundred years.
Not until Dietrich of Freiburg in the 14th century. It just shows you. Even a revolutionary genius like Haytham can be held back by the gravity of the old ideas. He had the right experiment, but the wrong conceptual lens for that one problem.
But his work on atmospheric optics, that was a totally different story. Pure breakthrough.
Oh, yeah. He was one of the very first to rigorously study and explain atmospheric refraction, the way light bends as it passes through the air. He used it to explain why the sun and moon look all distorted and weird when they're near the horizon.
A huge problem for astronomers at the time.
A huge problem. And
Yeah.
you mentioned that a contemporary of his took that idea and just ran with it to an insane degree.
Right. This guy, Al-Jayani ibn Muad, over in Cordoba, he takes Haytham's idea about refraction and uses it to calculate the height of the atmosphere.
It's one of the most brilliant pieces of applied science from that whole period.
How on earth did he do that?
He focused on twilight. You know, that period between the sun setting and it getting totally dark. He realized twilight is just sunlight scattering and refracting through the upper layers of the atmosphere.
Okay.
So he measures the angle, he waits for the exact moment the sun disappears below the horizon, then he keeps watching until the very last trace of twilight vanishes. At that precise moment, he measures the angle of the sun's depression below the horizon.
And what did he get?
He calculated it to be 18 degrees. And based on that 18-degree angle and the known geometry of the Earth, he calculated the height of the atmosphere to be about 52 miles, or 84 kilometers.
That's astonishingly close.
Yeah.
For the 11th century, using just his eyes and geometry.
And it all started with Ibn al-Haytham's initial work on refraction. It's a perfect chain of knowledge.
Okay, so let's get back to the core quest. The ground theory, the 4 conditions for seeing distance. Lay them out again, but let's really dig into what each one means.
You got it. So Haytham's theory is that seeing distance isn't some abstract instant calculation. It's a process, and it needs 4 things to be true.
Okay, condition 1.
Condition 1. The distance has to lie along a continuous surface. You can't accurately judge the distance to a star or just a random point floating in empty space. You need the ground, the connection between you and the object.
So if I'm looking at a boat on the water, my perception is actually less accurate than if that same boat is parked on a pier, because the water is less of a solid surface.
Precisely. The surface has to give you continuous visual cues, which leads to condition 2. That continuous surface has to be visible.
Right.
If it's super foggy, or if you're in a total whiteout from snow, your sense of distance just collapses, because the visual continuity is gone. The eye can't measure what it can't see.
That's why driving in a blizzard is so terrifyingly disorienting. You lose the ground.
You lose the ground. Now, condition 3, this is the really revolutionary one. Distance magnitudes have to be perceived and calibrated through bodily interaction.
Walking and reaching.
Walking, reaching, physical engagement. The knowledge of distance isn't born in you. It is learned by your body moving across and interacting with that surface over and over again.
Okay, hold on. What about people who can't walk? If the calibration depends on that physical history, how would they ever perceive distance accurately? I mean, doesn't that seem like a pretty big flaw in the theory?
That's a fantastic question, and one he didn't fully get into. But the theory really operates on the idea that human vision develops alongside our ability to move. For Haytham, the body's memory of measuring itself against the ground is what creates that initial mental ruler in your head.
So it's not just optics. It's embodied cognition. Is your physical history written into your brain's geometry.
Exactly. Your sports analogy was perfect. You don't just know the distance to the free throw line in some abstract way.
No, your body knows it.
Your body knows it from thousands of repetitions. That's condition 3. And finally, condition 4 is just common sense. The distance has to be moderate.
So it has its limits.
It has its limits. If something is miles and miles away, you can't see all the little bits of ground in between. The object itself is just a blur, and your distance perception becomes a wild guess. The theory is rigorous, but it knows its own physical boundaries.
What an incredible theory. It's physical, it's empirical, it's calibrated by your own body. And you said after it was translated into Latin, it dominated European science for nearly 400 years.
It was the textbook.
So here's the big question. If it was so good, so robust, why did we stop using it? What happened?
And that's the craziest part of the whole story. It wasn't disproven. It wasn't torn apart in some great debate. The sources say it was quietly abandoned.
Just forgotten.
It was superseded by something more convenient. The whole intellectual world just shifted under its feet.
And the person who caused that shift was Johannes Kepler.
Yep, Kepler. In 1604, he publishes this work, and in it, he proposes a totally different model. See, Kepler was mostly worried about astronomical errors. He needed a simple, abstract way to think about huge, empty distances in space.
And his big idea was?
He said we perceive distance based on the convergence of our eyes. binocular vision, a kind of natural internal geometry.
So wait a minute. Haytham's theory depends on the physical, textured, continuous ground calibrated by walking. Kepler's theory depends on abstract, empty mathematical space, calibrated only by the internal geometry of your two eyes crossing.
It was a total conceptual coup. Kepler's theory gave scientists a simple triangulation model that was way easier to calculate for astronomy, and it fit perfectly with the new Newtonian idea of the universe as this vast, empty coordinate grid.
So the ground theory didn't die because it was wrong. It died because it was philosophically inconvenient for the new physics.
Exactly. It got demoted. It became just a set of secondary pictorial cues, but its core radical claim that distance is known via the ground itself, that was lost. It just faded into historical obscurity.
Which brings us to the most unbelievable part of this whole thing, the 900-year echo.
It's one of the most stunning stories in the history of science. You fast forward all the way to the mid-1900s. There's this incredibly influential American psychologist, James J. Gibson.
J.J. Gibson.
And he's studying perception, and he's really unhappy with the abstract Kepler-style theories that were dominant. So he works for years and independently develops this comprehensive new theory of distance perception. And he puts the continuous, textured, visible surface, the ground right at the absolute center of it.
He actually called it the ground theory of space perception.
He did. He presented it as this radical reformulation of everything that came before, having absolutely no idea that he was perfectly echoing a rigorously defined 11th century scientific principle.
He accidentally rediscovered a 1,000-year-old idea.
An idea that was buried not because it was wrong, but because science had just shifted its preference toward abstract math.
That's profound. It suggests the history of science isn't some straight line pointing up. Sometimes we just take these weird sidesteps and leave powerful, true ideas behind because a simpler, more fashionable model comes along.
And that brings us all the way back to Farabi. Because we have to realize, Haytham's whole experimental revolution, it was only possible because Farabi had done the hard work of standardizing the language of reality decades before.
The definitional order makes the empirical order possible.
Precisely. His clear definitions of Jawar and Mada, his classification of the sciences, that was the common ground that allowed thinkers like Ibn Sina, Maimonides, and Averroes to build their work. You can't start an experiment until you agree on what the words for your equipment mean. Farabi built the universal standard.
And for Farabi, that was never just an academic exercise, right?
Yeah.
He believed all that abstract knowledge had to be applied in the real world.
That was the ultimate point for him. His political philosophy in works like The Virtuous City was all about this. He argued that the ideal ruler has to be a philosopher, someone who not only understands reality, but uses that knowledge to create order and health in society.
He used a medical analogy, right? The philosopher as a kind of doctor for the state.
Yes, a political physician who is healing the souls of the people. For him, organizing knowledge, defining terms, using logic, those were all tools the ideal leader had to use to diagnose and fix the problems in a city. Knowledge wasn't for a library shelf, it was for action.
Wow. So we started with a vocabulary crisis in Baghdad, and we end up with a theory of vision that crosses centuries, gets lost, and then rediscovered 1,000 years later.
And the thread connecting it all, from Farabi defining Jawar to Ibn al-Haytham defining distance, is this absolute insistence on structure first. The very structure of our knowledge, whether it's how we classify science or how we literally see the world, it's defined by the tools we choose to use.
Farabi's choice of words made certain arguments possible. Haytham's choice to focus on the physical ground defined what was measurable for 400 years, right up until Kepler's abstract math just took over.
And that tension, that conflict between Kepler's abstract geometry and Ibn al-Haytham's embodied, physical, grounded reality, that's not a settled debate. It's still at the heart of modern neuroscience and robotics. How much of our sense of space is innate geometry and how much is learned by literally bumping into a textured world?
So what does this all mean for us right now?
It means that every single time you look across a field and judge a distance, you're using a physical principle that was rigorously defined in the 11th century. A principle that got lost because a cleaner, simpler, more mathematical model just seemed more convenient at the time.
And as really as the final thought to leave you with, how many of our so-called modern breakthroughs are actually just quiet rediscoveries?
Exactly. How many other ancient empirical secrets about how we experience reality are we missing simply because they don't fit neatly into that abstract, mathematized world we've been building since the 17th century? What's still buried under the convenience of a simple equation? Something for you to mull over next time you take a walk and really feel the ground beneath your feet.
Absolutely. Thank you for diving deep with us. We'll see you next time.